now I'm going to continue talking about other data structures that we can use to implement a set ADT. Actually, before I do that, there is one quick thing I want to show. I didn't actually test out this key error method. So if I try to remove something that's not there, for example, the string, so if I try to say mySet.remove 173, that is not in the set here. So I actually get an exception with the message that I programmed in there. So this is very, very nice, very good practice to put things in there, safeguards, to help your users if they make a mistake. Okay. But anyway, so let's talk about how good this is as an implementation of a set. So let me think about if there are n elements. So let's say that there are n elements in the set. How long will each of these operations take as a function of n? So contains is going to loop through everything, potentially. We might get lucky, and the thing that we're looking for is towards the beginning of the array, but in general, in the worst case, so maybe I'll say, in the worst case, how long do these take? So in the worst case, we're going to have to loop through all n elements, right? For the add method, well, step 1 is actually to make a whole new array. So that takes n plus 1 steps. So we'll say, so because that's as big as the chunk we need to take out of memory. We have to copy everything in. That takes another n steps. And then we add this new thing at the end. So it's n plus 1 to make the new thing, and then another n plus 1 to put everything in there. And we reassign a pointer. I'll be a little sloppy and I'll say it's about twice n, okay? So about 2 times the number of elements that are in the list there is how long that takes, okay? Removing, which you just did, is a similar story. I have to create a new array with 1 fewer element, which takes about n operations, and then I have to copy over pretty much everything. All right, so that's also going to be about 2n operations. So this is not awesome. Okay, this is pretty slow. So for example, if I were going to add k elements to the list, this would take, about 2 times 1 plus 2 plus 3 plus 4 plus ... plus k. And if you recognize this, this is a triangular number. So this turns into 2 times k plus 1 over 2, which is equal to k times k plus 1, which is about equal to k squared. Okay, so this is going to be quite bad as we add more and more elements. It just takes longer and longer and longer. So the question is, can we do any better? Well, in class, in the first lab, we spent a lot of time talking about how we can do much better in search, at least, if our list is ordered. And that's where we do binary search. So let's go ahead and look now at an ordered list data structure for set ADT. All right. So what we'll do now is we will keep our array, so I should say array, not list. We'll keep our array in order as in invariant. Okay. And then we'll be able to efficiently search it with binary search. Now I'm not going to implement binary search here. What I'll do is I'll use Python's version, which is implemented in something called bisect. So Python implements binary search for you. Once you've mastered it on your own, you can just use Python's version. So let me show you an example. So if I were to make a random array of 100, well, let's say maybe 50 ints, 50 ints from 0 to 100. And let me go ahead and sort that. Let me seed it too, so I keep getting the same results. Same results each time. So let's see, what did I end up with in this array? So here's a sorted array. Okay. Now, if I use the bisect method, so I'll say bisect. Actually, this is a package. So there's a method within it called bisect left. If I say, okay, let's say that I wanted to look for 19, for example. Actually, let me go ahead and save this in a variable. So let's see what index does it give us and what is at that index. So here it gives us index 5, 0, 1, 2, 3, 4, 5. So that's the first index that this occurs at. That's what it's always going to give us. If I look for something that's not there, let's say 24, that will give us here index 10, which is actually where 25 is. So if I look for something that's not there, so if it's there, it gives me the index right after the first occurrence, right? Because there can be duplicates. If it's not there, it gives me the index right after the element that's above it. All right, so here I was looking for 24. 25 is the closest element that's right above it, so it's going to give me that index. Okay, so that's very convenient because it's basically exactly where I need to insert this if I'm maintaining things in sorted order. So what I'll do is let me take this class and I'll modify it to use an ordered array instead. Okay, so I've got it first. I'll change the contains method, and this is one that I can make a heck of a lot better by using binary search. So let me call this ordered array set. So what I can do is use that bisect method. So whichever object I'm looking for, if I assume, I have to assume that array is sorted. This is my invariant. That's what we call it. And okay, so I'll look for this thing. And what I'll do is, okay, so it is possible if I look for something that is at the end of this. So let's say I was going to look for 200. Actually, I'm going to get an out of bounds because if I look for 200, it's going to give me the index right beyond the thing that's closest to it, which is actually out of bounds here. So let me just say if this index is less than the length of the array, then what I'll do is I will look and see if, and actually I guess I better also check to make sure the array is not empty. Okay. So if the element at this index is equal to the element that I was looking for, then I found it. Okay. So this is going to do a binary search, and we're just checking to see, hey, did we actually find it? Or did we just find the thing that was the closest to it above it? All right. We do, though, have to do a little bit more work and add to maintain this sorted order. So we need to maintain the sorted order. And so what we'll do is, well, it looks like, I guess I already wrote this code ahead of time. But what we're going to do is find the index where it goes, or where it should go, okay, if it's not already there. And we'll copy over everything before that index, then we'll put it where it should go, and then we'll copy over everything that was above that to be after the index. Okay. So let's just first see if this works, and then maybe I'll write that again in a clearer way. Okay, so it seems like it worked. So I added a whole bunch of stuff to the set, and it behaved as it did before. Now just to check, let me print the underlying array. I can do that. Nothing is private in Python. And so I notice that this array is in sorted order. So actually this is kind of a free way to sort a whole bunch of numbers, right? You just add them and maintain them in sorted order. Let me write this in a slightly clearer way. This is the way I would do it with NumPy using slices, but really what I'm saying here is, so keeping in mind that the index is going to be the largest, or the element that's the closest to object, but greater. Okay, So what I need to do is copy everything up to but not including the index into this new array. So I'll say for I in range idx. So up to but not including the index, I will copy over what was in the old array. Okay, this line can stay the same. And now what I'm saying, just to make this, I think this line is probably particularly confusing if you're not really used to slices. So here I'll say for I in range, I'll say starting at idx up to but not including the index at the length of the old array. I'll say new array I plus 1 is equal to array at I. Okay, so I'm copying things. It's like I'm saying, okay, everything, you know, at index 0, 1 up to but not including the index goes in there, and then my index, and then everything else gets shifted over by 1 after that. All right, so everything has to get shifted over by 1 up to n. Okay, so we'll say it like that. So this is really writing out what's happening there. But once you get used to slice assignment and using NumPy, this is a NumPy thing, not a Python thing in general. This is a very efficient way to do it. Okay, so I think we have our ordered list. So let's look at the behavior here. And let's compare. So if I just move this table down and have a look and make a new entry here. So how does the sorted array stack up? So let's format this table a little bit for a second. Okay, so contains, how long does that actually take? Well, now I'm using binary search, right? So I'm continually having this. It's sorted, so I can do that and continually rule out half. So contains is much faster. So it's log base 2 of n. That's a heck of a lot better, right? Add is still going to be about the same. We do actually have a little bit of overhead now too, because we first have to find the index where we're putting this. So it's a little bit of overhead, but actually that overhead with the log is nothing compared to the n that it takes to copy everything, to make the new array and copy everything over. Whoops, I meant to put this down here. Okay. And it's going to be the same story for remove. Okay, so for remove, we're going to have to figure out the index where it currently exists, and then we're going to have to copy everything over, removing it. All right. So just to see, here's what we're looking at now. But you know, add and remove are about the same. The 2n is the dominant term here. But we got better with the contains. That's great. So binary search is helping us. I would say this is an improvement over an unordered list. All right. So we're doing better there. There is another data structure that we talked about in class that we can use. I hate seeing error messages here, so let me just get rid of this real quick. I'll go back and search for something that's actually okay. There is a data structure that we had in class that we can use, and that's the linked list. Okay, so I just copied in the code that we wrote in class. I'll gloss over some of the things that we did. The one thing that I didn't finish, I'll show you real quick, was the remove method. I did tell you the algorithm for it. You know, what you do is you walk along. So let's say that the linked list was like this. You create a cursor that starts off where the head points. You walk along until the next element is the thing you're trying to remove. And then the way that you remove it is you reroute the next arrow around to the thing that follows the next. Okay. So with that in mind, let's see if we can implement this. I'll kind of keep this picture off to the left here and maybe write a little bit of code. So let's see, can I get this all on here? All right. Trying my best here to fit this all on. Okay, so here's where I'm going to remove some objects. So what I'll do is I'll create my cursor at the head. So I'll start off at the beginning of the linked list, right here. And first, I mean, I should make sure that the head is not actually null. So, or none rather. So I'll start the cursor off at the head, and I'll say while cursor.next is actually, while the cursor actually points to something, right? Because I can't reroute this around the next thing if the next thing isn't even there. So I'll say while there's something actually there, and it's not the thing I'm looking for. So I'll say current.next.object. The wrapper inside of this is not what we're looking for. Then I have to keep going. So I'll move the cursor along. So I say cursor equals cursor.next. All right. So if I've made it out of this loop and the cursor actually has a next, then that means that I found it, right? There's two ways to break out of this loop. I either run off the end of the list, in which case this is going to be none, and I'll break out a loop, so I didn't find it. Or I found that the next thing was going to be the object that I want to remove. That it contains the object that I want to remove. So in that case, I have to reroute the arrow. So before the next, let's say I was trying to remove tray here. Before the next arrow pointed to tray, so I just found that the next is pointing to the thing that I'm trying to remove. I will say, let me reroute that to what follows tray. So I'll say, all right, cursor.next is going to be rerouted to be cursor.next.next. And actually the Python garbage collector takes care of everything here. All right? Otherwise, I ran off the end of the list and the thing that I was trying to remove isn't there. So I guess I'm going to raise that exception again. So I'll say, you know, this object is not in the list. All right? And actually, the linked list, the structure here is very nice. So now I'll move back to just the full code here, and we'll work with that. The linked list structure is quite nice because it can deal with general purpose objects. They don't even have to be of the same type in that list. So here's the example we were working with in class. Let's make sure it runs. Okay, so here's our linked list. Now let's test the remove method. So maybe before I look at the contains, I will try to remove. So let me say, you know, I'll add a statement here that's looking for tray. It says true to begin with, but let's now say my list.remove tray. And so now I notice that tray disappeared from the list when I printed, and it says false. All right. So cool. That's the remove method. So study that. That's the trickiest one. You'll have to use this in the first homework. But now what I'd like to have you do is, okay, so actually I should show you first. Now what we're going to do is wrap. Okay, so this is just a linked list class by itself. We need to use this to implement our set. So maybe now I'll call this linked list set. And so rather than using an array, I'm actually going to say self.mylist equals linked list. And so now I can just wrap around all of those list methods. So I'll just return self.mylist.contains object. So I'm creating what's called a wrapper class. I'm just wrapping around a list, but kind of translating the names of these methods here. So here I'll say, you know, self.mylist. Now when I'm adding something, here's where I might deviate a little bit from my behavior in the past. When I add something, I'm going to use the add first method because that's really fast, right? So when you want to add something, I'll just add it to the beginning. And I'm going to get a little lazy here and say, hey, maybe we can add with duplicates. So I'm not going to check to see if it's there first. I'm just going to add it straight to the beginning and be a little bit greedy because that is so fast. Okay. And maybe I'll have duplicates, but I hope you don't add too many. Okay, so that's kind of the decision I'm going to make for now. And then the remove method, well, I'll just call remove object. But this is what I'm going to have you fix in a little exercise here, because I actually want to change the linked list to remove all copies, since I can now have duplicates. Okay. But let's go ahead and just test this again on some of these examples here. So now I'll just change this to linked list set. But all the methods should be the same. So yeah, this seems to work. If I wanted to, I could drill down into that and print out what is in the linked list. So I would say print my set dot my list dot the method was, oh, it's print elements. Okay, so I don't need a print. I'm just going to call that method. So here's what is in the linked list that is working behind the scenes to make this set happen. All right. And just to show you, look, if I add an element twice, like 2, that can be in the list twice. And so I have to be a little bit careful, because the remove method's not going to completely work. Because now if I remove 2, it's going to remove one of the 2's, but it needed to have removed both of them. Okay. And I'm just realizing here I forgot a special case with the remove if it happens to be the first element. It should have actually removed the first element there. So I had a little bug in my linked list in the remove method. There's a special case. So if I start off with the object to be removed being the first one, then I should just call the no, I guess I have to do something special here. So I will say, okay, actually all I have to do is say self.head is equal to self.head.next. Okay, so this is a special case, the way I've written it. So like if I was going to remove Levi here, I would just reroute the head to be, well, see, I hadn't moved Trey yet. Change the head to be Trey. All right. And so now nothing points to Levi anymore, so Levi will get cleaned up by the Python garbage collector. Okay. Okay, so I did have a special case there. Now let's run this again. If I added 2 twice and once was at the beginning, now it actually removed. Hang on a second. Oh yeah, okay. Actually, it's the 2 that I added at the end, because I'm doing add first. Okay, that's the one that I want to end up removing here. Okay, great. Okay, we got a little mixed up there, but I think we finished strong. Okay, so this is the remove method, definitely the trickiest out of the 3 for the linked list with add first, contains, and remove. So I'm just going to have you tweak this method a little bit to remove all copies. All right? And then we'll continue. Real quick, one last little thing. So I now need to update my table and say, what was the point of doing all this? So when I implement the set with a linked list, I end up, okay, so contains still takes a while. It takes end time. I can't do this quickly because it's possible that the thing that I'm looking for is all the way at the end of the list. And if it's not there, I have to walk through the whole list, right? If I go look at that method in the linked list class, I might have to walk through the whole thing, right? The add method, though, is very fast. I'm going to say basically one operation. It's a little more than that, but basically constant time. In other words, it does not depend on how many elements are in the set. Because I've decided to tolerate duplicate elements, I always add to the beginning, no matter what, and that's extremely fast. So that's great. The remove method is going to be n, basically, because I have to find where the thing is first that I'm trying to remove, and then I remove it. But luckily, unlike the array, I don't have to make an entirely new linked list, so it's n instead of 2n. So you can see this is also an improvement in some ways over the array. But it does seem like a bit of a game of whack-a-mole because, okay, in the sorted array I was able to make the contains faster. In the linked list I was able to make the add faster, but the contains got slower again, right? So hopefully, and we'll talk about this in class, we'll be able to make the contains, add, and actually even the remove much faster. So far we haven't been able to do much about the remove, okay? So that's what we're moving towards here.